Hello and welcome to this first part in statistics in chemical measurements. So this is where we're going to start talking about things like normal distributions, standard deviations, means, and some statistical tests to see whether or not there are significant differences in our data. So the outline of what's going to happen is that we're going to be looking first at Gaussian or normal distributions. Then we'll move on to a comparison of standard deviations with the F-test, talking about things like confidence intervals, the range of data points or data values that can contain the true values for the data, and the comparison of means with students' t-test. So a normal distribution looks much like the figure on the right, where we have this curve, which is perfectly symmetrical about a mean value, in this case, 0. And so the distribution, so the curve goes from 0 on one side, around about -4, all the way to 0 at minus or to +4 on the other side. And this is perfectly symmetrical around the mean. So experimental measurements of a quantity often follow a normal distribution. It's sometimes known as a Gaussian distribution or a Gauss distribution, or even a Gauss-Laplace distribution. And so many experimental measurements will take this form if you conduct enough measurements. And whenever we try to fit the data, it often conforms to this kind of normal distribution. There are some times when it doesn't, but generally it does. Measured mean, the x, gets closer to the true mean, mu, with increasing numbers of measurements. So the amount of uncertainty or the difference between the measured mean, i.e. the mean for our samples or our measurements, will get closer to what is the true mean as we increase the number of observations or measurements that we make. So here is a figure at the bottom of the slide, which shows how the number of experiments, n, changes the appearance of our distribution. As the number n gets larger, our distribution appears to conform better to this idea of a normal distribution. So you can see here as it goes through 16, 32, 64, and so on, we end up with a much smoother distribution on either side of the mean value. The mean value will always be this kind of peak position here. So standard deviations, sort of the variation about the mean, alters the shape of this normal distribution. So as the standard deviation gets larger, we see a broadening of the peak. So this blue line here has a very sharp peak in comparison to the red and yellow lines, or red and gold lines. And that is because it has a smaller standard deviation, i.e. the values in our sample or population of our samples has values which are very close together, which reduces this standard deviation. The area under these curves is also proportional to the probability of finding a value in that region, and we'll talk a lot more about that as we go through. So for n measurements, the standard deviation can be calculated with this equation, where the standard deviation S is equal to the sum of all of the x values minus the mean of those values squared. And then that's over the degrees of freedom, which is n minus 1. So you'll see this n minus 1 quite a few times as we go through here. This is the degrees of freedom in the data. So the coefficient of variation is the standard deviation expressed as a percentage, and it comes from the mean. So the coefficient of variation is 100 times S over the mean given there. So here is an example of how we would go about calculating the standard deviation for a data set such as this. So we're asked, what is the average standard deviation and coefficient of variation for the data 5, 10, 15, 11, and 12? So first we calculate the mean, and the mean is just the sum of all of the values in our data set. So that's 5 plus 10 plus 15 plus 11 plus 12 divided by the total number of observations, or the total number of numbers, which in this case is 5. So it then works out to be about 10.6. Our standard deviation then is calculated using the equation that we saw previously. So it is each one of the individual data points minus the mean of the data set squared so that we get the absolute value. And then that's going to be over the degrees of freedom, which is 5 minus 1. And then all of that will be taken under the square root, and we will get a value of 3.647 as our standard deviation, which is quite large and probably caused by a few outliers in our data, this 5 and this 15. Now, the coefficient of variation for our data is going to be 100% times S over the mean, which is going to be 100% times 3.647, which is our standard deviation that we calculated here, divided by the mean, which we also calculated earlier. And that gives us a coefficient of variation of 34.4%. So standard deviation and how this relates to probability. So on the figure on the right is the figure that we saw earlier, which was a normal distribution about the mean. Now, in this case, we've now labeled different segments as multiples of the standard deviation. So this is one multiple of the standard deviation, this is two, this is three, and so on. And we have calculated the area under these, and that is going to be a fraction of the total area of the curve, under the curve. And so these are going to be, those areas are going to be proportional to the percentage probability of finding a data point inside that segment. So that's the equation for a Gaussian curve. You can use that to fit your data if you have data that would be fit well with a Gaussian curve. If not, you can also utilize various software packages that can do that for you. So the maximum of this curve occurs whenever the mean is approximately equal to the true mean for the value. And so the probability of observing a value within a certain interval is going to be proportional to the area of that interval. So as you can see here, the area under this segment is much larger than, for example, this segment, which means the probability 34.1% is going to be much higher than it is going to be for this area, which is 13.6% chance. So the probability of finding the value that we are observing between the mean plus or minus one multiple of the standard deviation is going to be about 2/3. So about 68.2% of all values are going to fall within this range from -1 to +1. So we can express these deviations from the mean in terms of multiples of the standard deviation, and we'll label that Z. So our standard deviation is S, and this is going to be Z for each one of our segments. So for example, 0 to 1. And so Z has this approximate relationship with the X value and the mean and the standard deviation. So X minus the mean is going divided by S is going to give us our Z value. Now, when Z is equal to 2, then we are 2 standard deviations away from the mean. And so that would be here. So each one of these numbers represents a multiple of the standard deviation. So this is 1 standard deviation away from the mean, and this is 2 standard deviations away from the mean, and this would be 3 standard deviations away from the mean. So the probability of measuring Z in a certain range is equal to the area of that range. And so, for example, the probability of observing Z between -2 and -1 is 13.6. It also happens to be between 1 and 2, 13.6. And this is related to the area under that curve in that segment, bounded by these multiples of the standard deviation. So the standard deviation S is a measure of the uncertainty of individual measurements, and it sort of tries to describe how much the measurements in our sample, how much they vary and how much they differ from the mean for that sample. So the standard deviation of the mean, sigma n, is a measure of the uncertainty of the mean of n measurements. So here is the standard deviation of the mean, and that's equal to the true standard deviation, sigma, divided by the square root of n, where n is the number of measurements. So because of this relationship, as we increase the number of measurements, we're going to decrease the uncertainty as a factor of the square root of n. So by increasing the number of measurements, uncertainty is going to be reduced. So for example, if the number of measurements increases fourfold, then n is going to be equal to 4. We have a square root of 4. Square root of 4 is 2, which means that we're going to end up having the uncertainty in the data. Instruments with rapid data acquisition allow us to average many experiments in a short time in order to improve precision. So this allows us to get closer to the true mean, because the only way to get close to the true mean is by having an almost infinite number of measurements on our sample. Of course, that's not really possible in most situations. And so what we have to do is we have to make do with a limited number of measurements. So the F-test is a way of comparing standard deviations, and we utilize this whenever we have, for example, the same sample measured by two different instruments or other uses. So the F-test determines if two standard deviations are significantly different from each other, and we compare those standard deviations only. So F calculated, so this is, we're going to calculate an F value based on our standard deviations. And so that's going to be equal to S1 squared over S2 squared, where S1 is always the larger of the two standard deviations, so that our F calc value is always going to be more than 1. So if F calc is going to be greater than F table, and there are a table of F values which can be looked up, and we'll see in the example as we go through how we can utilize those. So if F calc is greater than F table, there is less than a 5% chance that the two data sets come from distributions with the same population standard deviation. So here's an example of doing an F-test. So say in our workplace, an analytical, a new instrument has arrived. And so we want to see if there is going to be a significant difference in the results obtained from this new instrument compared to our previous instrument. So an analytical measurement is repeated on a new instrument. Is there a significant difference between the standard deviation of the substitute and the original instruments? So here is our data. So we have the original instrument and we have the substitute instrument. So the mean for the original instrument is 18.14. The mean for the substitute instrument is 18.20. S, the standard deviation for the original instrument, is 0.31 and 0.46 for the substitute instrument. For the number of measurements done on the original instrument were 6, and on the substitute was 4. And then the degrees of freedom, which is going to be n minus 1, that's going to be 5 for the original and 3 for the substitute. So here is our F calc calculation. So our calculated value of F is going to be equal to the square root of 1 squared, or sorry, the square of the first standard deviation over the square of the second standard deviation. So remember that we always put the larger standard deviation on top so that our F calc value is going to be greater than 1. So this then gives us a value of 2.20. Then we can compare that to the table values. And here are some table values for our are relevant to our system. So we have here the degrees of freedom for the first standard deviation, degrees of freedom for the second standard deviation. So this is the smaller standard deviation. And this is at a 95% confidence level. So if we have degrees of freedom are 5 for S2 and 3 for S1. So we read 3 down to 5, we get a table value of 5.41, which means that our calculated value is less than our table value, meaning that the hypothesis is rejected that S1 is significantly different or larger than S2. And so in our workplace, use of this analytical measurement should give us a similar true mean for our measurements. A second way, or an equally well utilized statistical test is the student's t-test. This is useful in comparing mean values in data. So the F-test was for standard deviations. The student's t-test is typically for mean values, but can be used in other ways. So the student's t is a statistical tool. It was developed by this person, W.S. Gossett. He worked as the head brewer in a famous Irish beer brewery, and he developed this statistical tool in order to help improve the brewing process. It's called Student's T-Test because he had to publish the results and this method under a pseudonym, which was Student, because his employer believed in the method, but was unwilling to allow it to be attributed to the company. But in this case, they released it because it was just so valuable. Normally, they didn't publish their results because they wanted to keep it a secret so their competitors wouldn't get an edge. So the student's t-test is used to find confidence intervals. So it compares mean values measured by different methods. And the student's t-table is used to look up t-values according to degrees of freedom and confidence levels. So this is much like the f values that we saw before. There are a table of values which can be looked up, quite easily found on internet search engines, and can also be found in many analytical chemistry textbooks, both T values, F values, and even, I suppose, in some statistics textbooks. So here are some T values for various degrees of freedom, only to the first 5 degrees of freedom, and at different confidence levels, 50, 90, 95, 98, and 99%, can even go up to 99.5%. So the most utilized are often 95 and 50%. So 50% is a much narrower definition of what a confidence interval may be. And so it produces a much narrower range of allowed values. 95% is typically the one used in most statistics today. So confidence intervals are important because they give us sort of the range of values inside of which our true mean is likely to exist. And if we choose, like, for example, a 50% confidence level, then what happens is we get a much narrower range for that true mean, but we also end up with some problems in maybe having an acceptable product in certain analytical chemistry settings. So to find the true population mean, mu, or the true standard deviation, sigma, many experiments are necessary. So this would be a large n value. Unfortunately, we often don't have the time or the sufficient samples to actually measure a very large number of experiments. So only the sample and sample mean and sample standard deviation can really be measured. But the confidence interval is a range of values that include the true population mean at a certain confidence level. So that range will increase if we have a higher confidence level. So like a 95% confidence level will have a much larger range of confidence interval than, for example, the 50% confidence level. So here is the equation for our confidence interval, or mu. And so that's going to be equal to the mean plus or minus TS over the square root of n. So this is our interval, or T constant. So TS, so T is the value that we get from the table. S is our standard deviation for our sample, and N is the number of measurements that we make. And of course, X bar is our mean for our sample. So here's the definitions. The confidence level or confidence interval example is given here. So what are the 50% and 95% confidence intervals for the data set 10.9, 12.3, 11.7, 13.0, 11.0, 12.1 weight percent glucose solution? So we've got a various weight percent sugar solutions. So we're going to first calculate the mean and the standard deviation for our data. So the mean and standard deviation are given here. It's often a good idea to utilize spreadsheet software if possible to calculate these, although for such a small data set, it's also possible to do this manually. T-values for 50% are read from our table that we saw previously, but you can also look it up. So t-values for 50% at 5 degrees of freedom is equal to 0.727, and for 95% at 5 degrees of freedom again is equal to 2.571. Now, why 5 degrees of freedom? Well, we have 6 data points in our data set, and so the degrees of freedom are always n minus 1, where n is the number of data points. And so if that is 6 minus 1, we will have 5 degrees of freedom. So our confidence interval then is going to be the mean plus or minus TS over n squared. So now we have all of the values that we need in order to calculate. So for a 50% confidence interval, we have the mean, which is 11.83, plus or minus this TS over the square root of n term. So T is taken from the table, it's 0.727 times the standard deviation, which is 0.734, all over the square root of n, where n is 6 because there are 6 data points in our data set. And so that's going to be equal to 11.8 plus or minus 0.2 weight percent. Then for 95% confidence, we do a very similar calculation. This time, the only thing that's changing is this T value, which is read from the table as 2.571. And so that means that it's going to be 11.8 plus or minus 0.8 weight percent. And so we can look at this on a number line where we have glucose weight percent here along the left-hand side, and we can see that this is our mean value, about 11.8. Then for the 50% interval, we have this narrow range here, but for the 95% confidence interval, we have a much, much larger range inside of which we are confident we can find the true mean. So the student's t-test can be used to compare mean values measured by different methods, and it can also be used to compare experimental results. So there are three different cases, use cases for the t-test in our analytical chemistry, broadly speaking. They are to compare the mean or the sample mean with the true mean, compare two means such as for mean 1 and mean 2, and then to look at paired data. So this is whenever we compare two or more methods on the same group of samples, but the individual samples should be different. So for example, say we have two methods, we get two samples from the same population, and then we would use those two methods to measure our two samples, and then those results would be compared as a paired data measurement. So how do we conduct a t-test? Well, first we have to make a null hypothesis, H0, and an alternative hypothesis, which is HA. So the null hypothesis, H0, is the difference explained by random error, and the alternative hypothesis describes the difference that cannot be explained by random error. So if the difference between the two sets of data is random, then the null hypothesis will be accepted, and if not, then the alternative hypothesis will be accepted. So first we calculate T, we'll see how we do that in a moment, and then we compare T with the T table at a given confidence level and degrees of freedom. Then if T is going to be less than T table, we accept the null hypothesis. And if T is greater than T table, then we reject the null hypothesis and accept the alternative hypothesis. So here are some of the important equations for our t-test. We'll see how these are used in a moment. So the first one is something we're already familiar with. This is our confidence interval equation, where the true mean is equal to the sample mean plus or minus TS over the square root of n. This is the second one. So we're looking at pooled standard deviations, or if the standard deviations are significantly different, then we have to utilize this version. So it's T is equal to the difference in the means over the pooled standard deviation. We'll see how to calculate the pooled standard deviation shortly. And then this is going to be multiplied by the looking really at the degrees of freedom in the data. So the number of, so it's going to be N1 times N2. So this is the number of data points in data set 1 times the number of data points in data set 2 divided by the sum of all of the data points. Or the alternative is this form, which is still the difference, the absolute difference in the two means. But this time it's going to be divided by the square root of S1 squared over N1 plus S2 squared over N2. And we utilize this whenever the F-test tells us that there is a significant difference between the two standard deviations. Then the third one here is whenever we're doing really the paired data calculations. So this is going to be T is equal to the absolute difference of the data from the two samples, and then that's going to be divided by the standard deviation of the difference times the number of measurements. Again, we'll see an example of how this is utilized in a moment. So then here are those equations which we don't yet know. So pooled standard deviation makes use of an F-test, or first of all, we do an F-test, and then if the standard deviations are past the F-test, i.e. the calculated F value is less than the F table value, then we can calculate this S pooled, which is calculated as so. So that's going to be the square of S1 times the degrees of freedom in dataset 1 plus the square of S2 times the degrees of freedom in dataset 2 divided by the degrees of freedom in the data. So that's going to be N1 minus 1 plus N2 minus 1. And then if we work that out, we get N1 plus N2 minus 2. And then this is the degrees of freedom, which will be utilized if we have significant differences in our data sets in cases 2 and 3. So the student's t-test then compares, as I've said, mean values measured by different methods. If standard deviations are not significantly different, i.e. determined by an f-test, then the pooled standard deviation can be used. If the standard deviations are significantly different, then compute the degrees of freedom and compute t. And if t is greater than the tabulated value for n1 plus n2 minus 2 degrees of freedom, then the two data sets have a less than 5% chance of coming from distributions with the same population mean. So that's kind of a summary of the t-test that we just talked about. So let's get into some use cases for the t-test. So a sample is measured several times. An average value and standard deviation are obtained. How do these values compare to the standard or accepted values? So in this case, you've got a certified standard for that or a regulated standard. And then you want to know if the measurements from your sample of a population are within sort of the range of that certified value. And so you want to compare those and see if you can accept your measurements. So here is an example of that. So a coal sample is certified to contain 3.19 weight percent sulfur. Sulfur is a pollutant. And so whenever coal is used as a fuel, you want to make sure the sulfur values are quite low. So an analytical method measures values of 3.29, 3.12, 3.35, 3.18, and 3.27 weight percent sulfur. Does the answer using the new method agree with the known answer? So the mean of the sample is going to be 3.242 weight percent, and the standard deviation is going to be 0.0818. So then we need to calculate the confidence interval for the new method. So we'll use our confidence interval equation. And if the known answer is not within the calculated 95% confidence interval, then the results do not agree. So typically, whenever we're doing calculations, if the confidence level is not stated, we typically accept it as 95%. So we'll utilize our confidence interval equation and we'll do the calculation. So for n measurements, there are going to be 4 degrees of freedom, which means that our t value from our table is going to be 2.776. So our confidence interval is going to be equal to the mean of the data plus or minus ts over n squared. And so at 95% confidence, we have 3.242 plus or minus 2.776 times 0.0818, all divided by the square root of 5, which is the number of measurements. So that's going to be equal to 3.24 plus or minus 0.10. And so at the 95% confidence interval, we have ranges from 3.14 to 3.34 weight percent, which just about includes the known answer, which is 3.19 weight percent inside of this 95% confidence interval. And so since the results fall within the confidence interval, they can be considered to agree with one another. And so in this case, we could certify or state that our coal is certified to that sulfur standard. And so it would, I guess, change the value of the coal, and it would also improve its or reduce its likelihood to pollute the environment. So in hypothesis t-test use case number 2, this is 2 different methods are used to measure the same sample, but give different results with different standard deviations. And we're asked, do the results agree with each other? And so that means, they're going to be different because we're using different methods, and that's okay for them to be different, but do they broadly agree where the true mean lies? So here, earlier on, we talked about a new instrument being added to our workplace. And we were wondering, or earlier we wondered, did the results differ significantly? And so we did an F test. So we can still proceed more and do a T test on that as well. Because the standard deviations passed the F test, it means we can use the pooled standard deviation. So our T value is going to be calculated using the pooled standard deviation equation, which is this, and our S pooled is going to be equal to this. And so we can get all the values for this from our table of data here. So our S pooled is going to be equal to this, which is the standard deviation of 1. If you recall earlier, standard deviation 1 was the substitute instrument and standard deviation 2 was the original instrument. So that's going to be 0.46 squared times 4 minus 1, which is the degrees of freedom of the substitute instrument, plus 0.31 squared times the degrees of freedom of the original instrument, all over the total degrees of freedom in the data, which is going to be equal to 0.373. And so the t value then is just going to take the values from this table where the difference in the means is here, the pooled standard deviation is here, and then we're looking at the number of experiments conducted. So it's going to be 4 times 6 for N1 times N2, and then it's going to be 4 plus 6 for N1 plus N2, which will give us a t value of 0.249. And so that would in fact pass our t-test. Then the last use case that we would typically encounter in analytical chemistry or instrumental chemistry is the measurements are made on 2 samples from the same source using 2 different measurements. We want to know if both contain the true mean or not. So this is the case where we have 2 samples from the same population, and we have done several measurements, at least 2, on both of those samples. And so we want to know if they both will contain the true mean or not. And so here we have mercury concentrations in 5 different fish samples were measured with 2 different methods. Is there a significant difference between the methods at 95% confidence level? So we have sample 1 through 5. We have methods A and B. We find the difference between methods A and B, which is the 4th column here, D. Then we find the mean for these differences, which turns out to be 0.298. And then we also find the standard deviation, which is going to be 0.149. So our t value is going to be equal to the absolute difference or the mean, the absolute differences. And so that's going to be 0.298 over the standard deviation of the differences, which is going to be 0.149. And then that's going to be times the square root of the number of measurements. So t is going to be equal to 0.298 divided by 0.149 times the square root of 5, which gives us a t value of 4.47. And so from the table, T95 for 4 degrees of freedom is equal to 2.776, which means that our calculated value is greater than the table value. And so we would reject the null hypothesis. That means that the differences in our data are not just caused by random error, and there is a degree of systematic error in the problem. And so that should be investigated. Okay, so now that we've gone through all of that, it's time to check comprehension. So how this works is I'll read out the question and then you should pause for some time and then we'll go through the answer together. So 2 methods are used to measure the same sample 5 times each. So the standard deviation of the first one is 0.42. The standard deviation of the second one is 0.31. And so when conducting a t-test on this data, is it possible to use the pooled standard deviation at the confidence level of 95%? All right, so pause if you need more time, have a go at this question yourself, and then we'll go through the answer together. Okay, pause if you need more time and need to think about this. So we're about to reveal the answer now. So this question asks if S pooled can be used. And so this is possible if the F test shows that F calc is less than F table. So we need to just determine if F calc is less than F table. That's all we're being asked to do really. So we see here that fcalc is going to be equal to 1.836. And so then we look up f table. So that's going to be 4 by 4 degrees of freedom, because we have the same sample measured 5 times each. So that means that we have 4 by 4. So that's going to be a value of 6.39. And so that means that fcalc is less than f table. And so that we can, in fact, use s pooled. And so that's the end of part 1. Come back for part 2 whenever we'll discuss outliers in data and things like calibration curves. Thanks for watching. I hope you learned a lot.